Okay, so the alkali metals, in their chemistry, of course, you can have the free metal. So lithium metal, in its elemental form, has an oxidation state of 0. As soon as you start doing chemistry of alkali metals, you're going to encounter those alkali metals in an oxidation state of +1. And that's quite important when it comes to assigning oxidation states of other elements in compounds. If you know that the oxidation state of your lithium or your sodium or your potassium is fixed at +1, it must be +1 in a chemical compound, then you can use that piece of information to deduce what your oxidation state of your other centres are. Now, what you're going to have is a monopositive charge on your ion. And because the positive charge is just 1, and you have an ion, then essentially what you have is a relatively low charge to radius ratio. And it's important to appreciate that the charge to radius ratio is a factor that controls the lattice energy. So what we have is a relatively weak monopositive charge on there. What also happens, of course, as you go down a group in the periodic table, what happens to the size of the atom, or indeed the ion? It increases. And because it increases, that means the positive, you've still got one positive charge. That charge to radius ratio is going to get lower and lower. Electrostatic interactions between these ions are actually greater for lithium than they would be for cesium, simply because cesium is much larger. Okay, so we have relatively weak coulombic interactions between cations and anions. And this means that you're going to have relatively low lattice energies. Relatively low lattice energies will translate into relatively low melting points for the ionic solids. That's the first thing you should recognise. So if you're going to have a lithium salt, it's going to have typically a lower melting point than a magnesium salt, for example, simply because the ionic interactions are going to be weaker because the charge is lower. It has another important consequence. Because the lattice energies are relatively low, what happens when you dissolve an ionic solid is you break that ionic lattice. You have to break up the ionic lattice in order to dissolve an ionic solid. And the weaker the ionic lattice, the easier it is going to be to break it up. So lithium, sodium, potassium salts are much more soluble than magnesium or calcium salts because of this factor, because of this lower charge to radius ratio, because the coulombic interactions are weaker. This means that these species are going to be much more soluble. Now, is alkali metals entirely concerned with hydrides and oxides? Well, of course, they're not. There are a huge number of alkali metal salts, and many of these alkali metal salts are, of course, very soluble. Nitride is an N3- anion. And the only way to stabilise an N3- anion is if you're going to have a really quite a small countercation to go with it. So you've got to have a very small, highly charged species that's going to go with that. Now, lithium is very unusual. Lithium will react with dinitrogen, and this will happen in nitrogen atmosphere. So if you exclude water vapour and you exclude oxygen, then lithium will react with nitrogen. And what it forms is lithium nitride. Lithium nitride is itself a black tarnish on the surface of the lithium metal. And it's quite unusual in doing this. Sodium doesn't. Sodium does not react with nitrogen. Potassium does not react with nitrogen. Even though these have lower ionisation energies, these elements do not react directly with nitrogen. Only lithium does. The nitride salts themselves, what you've got is an N3-, a very, very highly charged N3- ion. That N3- ion is carrying so much charge, it's such a strong Bronsted base that it will react with anything that's protic very readily. In the same way we talked about the hydride anion reacting very readily, the nitride 3- anion will react very readily. So lithium nitride will hydrolyse. So if you take a sample, cut it open in the air, then even if you get some lithium nitride being produced, because statistically speaking, air is mostly nitrogen, even if you get some lithium nitride produced, that lithium nitride is going to very rapidly hydrolyse and give you lithium hydroxide as your ultimate lithium compound.